Last time I finished on proving that pi1 of S1 is as a group isomorphic to Z. So now, so this is really, I mean, this is kind of basic, but really powerful fact. So let me consider one kind of fundamental application of this is what is called the following theorem, which is called Browser fixed point theorem. So the statement is the following. So let be a continuous map from disk to itself. Then there exists a point in the disk such that f of x, well, let me note it, x0. There exists x0 such that f of x0 is the same as x0. Okay, so what is the proof? So we want to prove it using the fact that we proved in the previous lecture. So we will prove it by contradiction. Suppose it's not true. It means that for any x0, for any x in the disk, f of x isn't equal to x, right? And suppose this is the case, then it follows that then we can define a continuous map, let's say H, from the disk to S1, which can be identified, this S1 can be identified as a boundary of this disk. And so let me define it, let me explain geometrically how we define it. So we take, suppose we take some x, so we want we take some x in the disk, so we take f of x. So here we use the fact, our assumption that f of x is not the same as x, so this are two distinct points, and then I can draw a line from f of x. Well, let me say we can draw actually an array from starting from f of x and going through x. So such since these two points are distinct, it's there is a unique array like this, and the intersection of this ray with the circle is let me denote it by x. So, I mean, I'm not going to write explicitly, but it's like from the picture geometrically, it's clear that such map is well defined. And moreover, it's easier to show that it's continuous, because if you consider any small perturbation of x, which will result in a small perturbation of x prime here on the boundary. Okay, and so we define the continuous map from disk to S1, and more ways we can see that if x belongs to S1 itself, to the boundary of a disk, then then h of x is the same as x, right? Because if x is somewhere in the boundary, the ray. So since we want to pick, since you want to pick the intersection of the ray with the boundaries, it must be the same as x. Right? Okay. So what we got here is, by definition, which we had in the first lecture, H is a retract from D to its subspace, topological subspace S1. Right? By definition, so retract is on the subspace is a continuum map, such that its restriction on the subspace is identity. Right? Okay. Now let me do the following. Take F to, okay, F is already used. So let's take G to be any loop in S1. And so now we see that we can show that G, so this can be considered the loop in S1, but since S1 is subspace of D2, this can also be considered as a loop in D2 itself. And it's easy to show that G is contractible in D2, if considered as a loop in D2, which means that it's homotopic to a point, and indeed such homotopy to a point can be explicitly constructed as follows. So the homotopy to a point so we can see we want to, so the homotopy should be of loops, homotopy of loops should be a map from a square to D2, and we explicitly define it as follows. So S here is a parameter along the path, and T is a parameter of homotopy. So we take it 1 minus T times G of S plus T times x0. Well, okay, sorry, x0 is already reserved. Let me denote x tilde. For any x tilde, so I can choose x tilde in particular to be in S1, the boundary of D2. So here I'm using it's so what I do here is if I take some loop here in the boundary as a disk, considering it's as a loop in disk, I can always contract it by doing this explicit homotopy to some context, right? So here these lines are trajectories of this vector. Okay. But then it actually follows that G is also contractible in S1 because we have a retract H from disk to S1, So one can construct a homotopy which stays inside S1 such that ST is mapped to, let's see, R. Just take a composition. What do we want? We want to take a composition of this homotopy F with R. Sorry, H. Right? So H is a map from disk to S1, or explicitly it can be written as false H. Well, this is F of S. Okay. And yeah, so that if I restrict myself with H, H time H composition with F at the end of my homotopy interval, it's the same as so H of X tilde, which is the same as X tilde, right? Because H is identity, H restricted to S1 is identity. And this restriction to the beginning of the homotopy interval is H of G of S, which is the same as G of S, right? Because G was a pass inside S1, and H is the identity when restricted to S1. So this means that any pass, any loop in S1 is contractible. But this is not true because we show that pi1 of S1 is Z, is not real. Pi1 by definition is a set of, as I said, it's a set of equivalence classes to homotopy. So this concludes the proof. So our assumption, our initial assumption is a false, and then there must be a point such that f of x is the same as x. Questions? Okay, and so there are other applications of this one, but today I wanted just to mention one. So let me, now I want to, so we consider it, we define the notion of fundamental group, we calculated consider a basic example, but now we want to consider some various, want to study various properties of this fundamental group, which in particular will allow us to calculate it in some other examples. So we want to show the following proposition, that pi1 of x direct product with I, well, it's a product of x and y topological spaces. Consider it with base point is a pair x0, y0, isomorphic to y1 x and 0 times y1 y. So here it's a product of topological spaces, and here it's a product of groups. So it's a nice property. You can like it's a product of spaces under action of y1 becomes a product of groups. So let us prove this. So we want to use as the following general fact. For any the following general fact, the function f, which from some topological space z to x product with y is continuous. So suppose it's explicitly is written down as follows. So it's z. So since the points here are pairs of points in x and y, so any function like this defines a pair of functions g and h, such that g is a function from z to x and h is a function from z to y. And the property, so from the definition of topology, of x times y, one can see that f is continuous whenever both g and h are continuous. So this is easy to see by directly the definition of topology here, which is generated by product of open set and the fact that the continuous function is such that the preimage of an open set is an open set. So let me not go in detail here. Okay, so this is a general fact which you want to use. So first, if you take in particular z to be an interval, it follows that any loop in x, any loop in x, y, that is a function f from 0, 1 to x, y, is can be interpreted as a pair of loops g, h in x and y respectively. So here again I define the loops g and h in x and y by default as components of my function f. And from this general statement, so if f is a continuous function, then g and I should be a continuous function. Then take z to be, if you take Z to be a product of intervals. So a map from a product of intervals. So in particular, a homotopy is a map from a product of intervals to the topological space, a path homotopy. Then, so it follows that, so if you use this general statement when Z is a product of interval, it follows that path homotopy X, Y is a product of path homotopy. X and Y. Okay, and then if two paths F and F prime are homotopic, paths homotopic X times Y. And so that if I write the decomposition into components in X and Y, F is a function. The values of F is the pair of values of functions G and H, and the same for G prime and H prime. Then it's equivalent to the fact that G is homotopic to G prime and H is homotopic to H prime. So this is homotopy, path homotopy in X, and this is path homotopy in Y. So indeed, so if this is F, this is some function F, this homotopy realized by some function F from the square to X, and this is by G and H. So this is just follows from this general statement before, and so that we can decompose F into a pair function G and H. Okay, and so then it's so it follows that there is a projection so that if I have some path here, which is so that the corresponding function has components G and H, I map it to the homotopy class of this function X and Y, of this path in X and Y, I map to a pair of homotopy classes in pi1 of X and pi1 of Y. So this shows there is projection, but we also want to show that it's actually isomorphism on the level of groups. So we want to show that this is respected by the product with multiplication of elements in the group. And so if you consider, so the multiplication is realized by concatenations of paths. So this is by definition is the product. But when we, I mean, by definition of the concatenation, since it's just like we kind of rescale, we combine. So minus, if we combine, if we want to define the concatenation G1 and G2, for example, if we combine these two functions together and rescale them by half. So the concatenation of two paths in x times y is the same as, so we can concatenate the paths in x and then concatenate them in y. And this is the same as by this bijection is the same as G1, G2, H1, H2, and this is the same as PDF of G1. So here we use the definition of the pi 1 in x and y separately. And this is indeed the definition of the product of elements in the product of groups. So this concludes the proposition. Any questions?
Question regarding ICTP. If we have two spaces, we have infinitely many, and we can use this infinitely product of topological spaces with either the product topology or the other kind, the box topology. In this case, there is also a relation with the product of the corresponding fundamental group, and if yes, do we take direct product or direct sum? Can this proposition be extended to infinite product of topological spaces?
Well, I think so, yeah, but
maybe if we take the product topology, we take the direct the direct sum, and if we take the box topology, we take the direct product. I don't know.
Well, so if you take, yeah, I think if you take product topology, it will be a direct sum. And if we take the box, yeah, it will be there. But yeah, I mean, let us consider just for fun. So let me consider. So let me state the following definition. Consider phi be a continuous map within the topological spaces x and y. Then we want to define a map phi prime, phi star by 1 of x with some base point x0 to pi 1 of y with base point f of x0. And we want to call this map as a pullback, sorry, push forward. Of phi. And it is denoted by phi star. So for any map phi, there is my phi prime, and it's explicitly defined as follows. So we take some path, some loop in X, represented. So there's a class in phi1 represented by loop F, and then we want to map it to a composition of phi and F. So F is a map 0, 1 to X. So we want that makes the following remarks. So first of all, the first remark is well defined. So phi star is well defined. So again, we show, so since we use, in this definition, we use some particular representative f, we want to show that this is not dependent on the choice of representative. So if f is homotopic to some other path f prime in X, then the position of phi with f is homotopic to the position of phi with phi prime, where the homotopy is just given by the composition of the homotopy here is phi. So if you take another representative, here we obtain a homotopic path, so it has the same class. Second property, second remark, which is due, is that phi star is not just snobby a map, but so this is a map between groups, and phi star is a homomorphism. So in order to show this, we want to show that phi star, so if we take a product of two group elements, so this is the same, so by definition of the product in the pi1, we want to replace it by a class of the concatenation of two loops. And so by definition of phi star, this is the same as phi class of phi composed with f1 concatenated with f2. And so this composition of phi with f1 concatenated with f2 is the same as composition with f1 and phi concatenated with f2. And this is a star f1 and star. So this shows that this is indeed homomorphism.
Sorry, do we put the star at the top or the bottom?
At the bottom. I mean, the top star has a different meaning. It's what is called pullback.
Okay.
What does it mean? Push forward?
Okay. So why is it push? Indeed, push forward? Because so if you have how can one diagrammatically show this? So we have some x, y here, and the map phi like this. So then the pass here, the passes in x are maps from the interval to x or to y respectively. So here if we take some pass in x, we can obtain a pass in y by taking a composition of f is phi, and so this is the indices as defined the map. So let me omit the base point. Okay. So then, if you have pass on x on the map phi, it's pushed to the map in y, and so phi star is so if it goes in the same direction between pi ones, it goes in the same direction as phi.
Are we going to eventually talk about the pullbacks?
I'm not sure. Because we will study homology later. For homology there is also an alcohol push forward, but for cohomology there is a pull. The analog of push forward is the push forward is replayable back.
Just that we have a function from y to some other space and we compose this with phi to get so we have maps from y to some other space. We have a function from this collection of maps from y to some other space to a map from x to this same space by composing with phi.
Yes. Well,
is that the pullback? It's just if given a function from x to y,
yes.
We have a function, induce the function from maps from y to some other space z to the collection of functions from x to this other space x.
Yeah, so, well, I'm not sure if this answers you, but I mean, the pullback indeed, if you consider, for example, some other space z, like here, interval or whatever, and you consider maps from x and y to this space, then this will give me so if I have a map here, so you have some sort of phi here, and I have some f here, then I can define here f composition of phi is f perfect. So I have so my maps from y to z. They transfer to maps from x to z. And then the maps go, so this is a pullback. I mean, in general, so you can write maps from. So for some fixed z, there is a map from x to phi, then this is a so that here is and the push forward in general, so indeed there can be not interval but anything. But I mean, for homology, it's not defined like this. But I mean, you can actually formulate. It's also this.
Use the home. The home of our category. Because usually it will be, these maps will be itself have some algebraic structure, and then we will have the increased map.
Here we're just using continuous maps. I mean, just like for, I mean, I don't want to go there, but for homology, just, I mean, the interval is replaced by some other complicated things. Okay, so. Okay, so what is the, so we want to show the following two properties of this push forward acting on fundamental group. The first nice property is that so if we take phi to be identity map from X to itself, then its push forward is identity on phi1 of X. And the second property, if let's say phi is a map from X to Y, and psi is a map from Y to Z, where X, Y, Z are three arbitrary topological spaces, then composition of phi and psi, the push forward of it, is the same as the composition of push forwards. This is the composition is of course is a map from phi1 x 0 to phi1 z. So first, well, it's first is obvious. So F. So if so, since we take phi to be identity on X, the composition of so the phi star it takes some homotopy class of some F and brings it to the composition of phi is F. And this is the same, since phi is identity, the same as homotopy class of F itself. So indeed phi star is identity on phi1. Now the second property. Let me do a diagram. so we have, suppose we have some path f in x. Well, by path, of course, I mean actually I mean loop. So f of 0 is the same as f1 in particular. And so consider map. I have a map from x to y, phi, and I have map psi from y to z. So then the loop f is pulled back to loop phi composition is phi, and then it's here. So if we do the same here, we get a composition of phi is psi is phi and f. But of course, this composition is the same, so we can first compose psi with phi and then compose it with f. All right. And here we have a phi star. Here we have so here, so this operation on the path induces the map on pi1, which is phi star. So then this operation, this composition is psi, gives a map psi star. But since we can directly go from x to z by just taking a position of psi composed with phi, this should be the same as composition of the psi composed with phi and then taking it back. So it goes this way or this way, doesn't matter. Then we show this property. So from one can say that from these properties, so for the one can say that pi1 is a function, what is called is a functor. So unfortunately, due to time, I'm not going to elaborate on this. But I mean, in order to properly define what is a functor, so we are not going to use it in lectures. But I mean, in order to properly define what is a functor, it's one needs to define the notion of category. But very intuitively, so here being on intuitive level, so pi1 can be understood as kind of so for we have a collection of topological spaces, and we map them to a collection of groups, so that for any topological space, we assign a group 1 of x, and moreover, so the fact that this is a functor means that so there is a natural maps between the topological spaces, so there are continuous maps. And the continuous maps here they translate it to homomorphisms here. Consider that continuous morphs y morphs to homomorphisms x. If you take phi here, element phi maps to phi star.
Homomorphism between pi 1 x and y? You mean homomorphism between x and y, or just pi 1?
Oh, sorry, yes, yeah, I thought so. Okay, now, so the following important property, so let R be a retract from logical space onto its subspace A. So let me remind you the definition of the retract here. So R, and also to fix the notation, so R, so we have a map R from X to subspace A, which is included in X itself, or we can define this composition R tilde such that so this kind of diagram commutes, and so that R tilde restricted on A is the same as identity. And this, let me denote this embedding map as R. Okay, then the push forward of the embedding, sorry, of the inclusion IA is injective. And moreover, if X deformation retracts onto A, then this push forward is an isomorphism. So let us first prove the first part, so that it's injective. And so take any loop F in X f is a map from the interval to x. And well, actually, I don't even need to take a particular loop. So I actually, just can deal with it.
Constant function into
Sorry.
A. The constant function into an element of A is also an element. Is also a constant function when viewed as a. I mean, if we have a function from I to A which is constant, and if we compose it with I, it is also a constant function into X.
Yes.
Sorry.
No, okay, so what I want to use, so I want to use direct, so I don't need to take any representative of pi1. I just want to use the form fact that the composition of IA, so this property R tilde restricted on A is identity on A. It's the same, can be written as a composition of inclusion and R is identity on A, right? And then it follows by the property we showed before that the pullback, so push forward of this guy, this should be the same as a push forward of this guy. But then the push forward of the composition is a composition of push forwards. And the push forward of the identity is the identity. So this identity of pi1 of A. So it's only can be the case. So if the composition of two homomorphisms is identity homomorphisms, can only be the case if the first one is injection. Because if it's not an injection in particular, it should map. If it's not an injection, it maps two different elements to the same element, so this composition cannot be a bijection. This must be an injection. So now the second part. So we want to. So now assume that there's a deformation retracts from X onto A. So this means that explicitly this means there is a function from X times interval to X such that f restricted on x times 0 is identity on x, and f restricted on x times 1 is R tilde. This is the definition of the accommodation block. So there exists a homotopy between identity and a retract map. Okay, and then yes, for this we want to so let us take any pass F. So any loop F in X and then we want to show that F is homotopic to a composition of F with R tilde, and indeed this can be explicitly realized by taking the homotopy H such that path homotopy H of S and T is explicitly given by F of F S and T. So indeed we can see that H of S0 is, so if T is equal to 0 here, so we restrict F when T is equal to 0, then F is identity, so this is the same as F of S, and H of S1 is the same as F of S1, and it's indeed using this fact, this is indeed the composition of R tilde with F of S. But so this so F is homotopic to a composition of R tilde with F, but we know that the image of the map R tilde is inside A, right? And which is a subspace of X, is actually not just inside, it's equal to A, right? And so we show that any path in any loop in X is homotopic to a loop X. And then, so how does phi star act? Sorry, what is this? So we want to show that IA is surjective. So indeed, so for any, so this is if you take arbitrary element of pi1 of X, this can be realized as as an image of some path, some homological class of some path in A. So of course, yeah, I forgot to mention that the point, of course, base point, we want to take base point to be inside. Okay, so in order to avoid various technical surpluses, let me also assume, so in the definition, in the formulation, of the composition, assume that X is postgraduate. Then all pi ones for any base point are equivalent, are isomorphic, and we can always choose a base point instead. Okay, so why is it true? Because by definition, this is a class, homomorphic class of R composed with F prime. And so here we can choose take F prime. So we want to show the existence of such F prime. We want to take F prime to be R composed with F. Until composed with F. And then this is the same as F, because so if I take restriction of R tilde, yeah, this composition is if I restrict it to A, this becomes, well, okay, sorry, let me So, yeah, so let me say it, it's better to say it this way. So let's, so if image of F prime is inside A, then so F prime is some path in 0 in some loop in X, then the composition with exclusion is the same as F prime. And, so I can take, so indeed I take F prime to the composition of F is R tilde, so this is the same as R tilde F. Composed with F. So this is true because the image of R tilde is in A, right? And moreover, we showed that this is this path is homotopic to F. So this is so indeed we showed that any element here can be realized as an image of push forward of IA of some element F prime.
So this proves this surjective?
Yes. So, oh, well, yeah, well, it's proves that these IR star is surjective, but we also already showed that this is injective. So this is part one of the proposition which we already proved. This means that R star is isomorphism. Now let me continue the following proposition, which so let me actually call it lemma because we will meet in the proposition in the next proposition. Okay, so let F be a homotopy between two maps, let me denote it by phi 0 and phi 1 from x to y. Then we want to show that the following diagram so the map phi 0 induces push forward phi 0 star to I1 y phi 0 of phi 0 and phi 1 induces push forward to phi 1 y phi 1 0 and the statement there is the following diagram is commutative. Where so BH is as was previously defined a map between fundamental groups of the same topological space, but with two different base points. So BH, this isomorphism, associated to the class H, where pass H is passing Y, such that H starts, let's see, at phi 0 x 0 and ends at phi 1 of x 0. You want to show the following statement?
One is path connected.
No, here x is not needed to be path connected.
For beta h to be isomorphic, don't you require y to be a path connected? Why?
Well, we will show that. I mean, there is. Okay, so I mean, this h can be explicitly written down. Actually. So this h there. I mean, it's true whenever such path exists, and it exists because we can choose explicitly h to be the following: h of s to be f of x0. So it's enough to show, I mean, this BH is defined whenever there is a path connecting two points. So if it's path connected for any 2 points, we can roll it. But in this particular case, even if y is not connected, the fact that we have this homotopy and this homotopy between f0 and f1, such paths between phi 0 x0 and phi 1 of x0 exists, because one can write explicitly this path is full, right? So when s is equal 0, this is indeed becomes the restriction of f at the beginning of interval, which is f0 of x0, and if s equals 1, we indeed have this. So we want to show, so what is the proof of this length? We want to show that, so what does it explicitly mean that this diagram is commutative? Is it just for any class of some loop f in phi 1 x and 0, so BH of phi 0 star f is the same. So this is what we want to show. Same as phi 1 star of f. F is a loop in x. And this is the quality. So this is equality in let's see, pi 1, 1, 1. So this means that, so what is the definition? So let me explicitly write the definition of the right hand side. This is the homotopy class of phi 1 composed with f. And the left hand side, so first, so this is, if you remember definition of BH, it's the following. So I take a composition of paths f with f0, and then I compose it with h bar, the inverse path of h and h. So in order to show that equality, we need to show that the corresponding paths are homotopic. Right? one can do this by just explicitly constructing such homotopy. So let me, before writing some formulas, let me draw some pictures. So we have some loop f in x, and it's mapped to some. So we map it to y, phi 0 or phi 1. So in the first case, we get some composition of, so this loop is mapped to the composition. Is f, and in the second case, mapped to composition here, f, and so this is my x0. So it's mapped to, here it's mapped, in the first case it's mapped to phi 0, and in the second case it's mapped to phi 0, sorry, phi 1 and phi 0. And so h was a path like this, right? It was connecting these 2 points in y. And so what we want, so in the first, so the left, so here, so we have, on the right hand side, we have this loop, phi 1 f, and what we want to do, we want to show this homotopic to the following, so path. So first we go along h bar, so the opposite of h, then we go along phi 0 composed with f, and then we go back along h itself. So we want to show this the homotopy between these two loops. And indeed it can be explicitly constructed by just explicitly transforming, like deforming this, the whole thing, to phi y composed with phi using my homotopy f. So let me write explicitly. So let me keep. So let t be this homotopy parameter. And I want to, like this fixed homotopy parameter, I want to consider it a function. I want to consider some a loop in y, right? With base point phi 1. So I want to explicitly say that this is the following. So this can be realized as a, so for fixed t, this loop can be realized as a composition of the following loops, ht, which I will define in a moment. Then the loop which is composition of phi with f. So here I keep my loop parameter to be kind of empty. So this is a kind of empty. This is the input of my function from the interval to my space, target space, and so here t, and then I compose it with opposite with the inverse of ht, where ht. So what ht is restriction of H from, so H goes from this point to this point, but I want to restrict it to, so it goes from phi1 of x0 to phi f of t of so this is, so if I draw this, so here is somewhere in the middle, so this is, if I start deforming t from 0 to 1, so this is somewhere in between. I have this path f composed with f, and the second variable is t, and this is how my path ht looks like. So explicitly one can write ht s as h1 minus t1 minus when t equals when t so when t equals 1, it just becomes the same as h of s. Here. This is the full path, and when t is equal to 0, this becomes just constant path thing here. And so when t varies from 1 to 0, it just slows down. Is this correct? So H. Sorry, no, wait a minute. So I want. So when t is equal to 0, I want to get this thing, right? So I want to get the full H. T equals. So if so when t equals 1, h1 of s will be the same as h of s, and when h0, so I want h. Sorry, no. At the zero t, I want to have this thing, right? So I want to have the full h of s, and at t equals 1. I want it to be constant. So when t equals 1, I want my path h collapses just to this thing, right? So I want it to be h of 0. So what is the proper scaling of parameters which gives me this? So I want to have something like 1 minus t times s. Okay. So yeah, so h goes like when t equals 0, it's h, when t equals 1, it's a constant path, so which you can just remove here. And for big F, of course, when t equals 0, we get this thing, and when t equals 1, we get this thing. So indeed, this gives us the desired format. So this concludes the talk of the lemma. And so with this lemma, so let me just quickly, one can very quickly prove the following proposition. It will take just a couple of minutes. Suppose a map from X to Y is a homotopy equivalence, then phi star is an isomorphism. So we already had this statement in a particular case when phi is a deformation effect, which is a particular example of homotopy equivalence. But this is actually true in general. So, so how does it works? So let me. So by definition of the homotopy equivalence, there exists a map, continuous map from Y to X, such that composition of phi and psi is homotopic to identity on Y, and composition of psi and phi is homotopic to identity on X. And then it follows, in particular, it follows that. So we use this properties of push forward with respect to composition and the fact that they push forward. So. And so the push forward of identity is identity. But so here, so we showed that. So we showed, in the previous level, we showed that if two maps if they're homotopy between two maps in X and Y, then it means that they are differ by isomorphism, right? So it means that this is an isomorphism. And from the other property, it follows that the composition in the other way is also an isomorphism. So to be more explicit, so if there's homotopy, this means that phi, so psi is equal to identity, the composition of some BH times identity plus right? Whereas this is the push forward of identity is identity, and BH is isomorphism, maximum fundamental. So this composition are isomorphisms, but so from the first, it follows in particular that this composition of two homomorphisms is isomorphism. Then it follows that phi star is subjective. And from this, the fact that this composition in this order is an morphism, it follows that phi star is injective. And since it's both surjective and objective, this means that it's ionizing.